Okay, we're now ready to start actually applying our matrices in our WebGL programs. Now, this is going to be span over a number of lectures, partly because we can apply the matrices in different places in either of the shaders or in the application. And so the functions will be a little bit different, and also we'll have to examine which is the best way to do that. And then, of course, we have to look at the different kinds of matrices, principally rotation, translation, and scaling. And also we'll have to look at if we animate that, if we want to do some rotations changing in real time. We have a camera moving that's changing its position as it goes through the scene, or objects in the scene we want to move over time. So all of those things are going to come in over the next 4 or 5 lectures. Now in this lecture I'm going to focus on sort of 2 things. One is how did OpenGL do this in the sort of the pre-shader, forced shader days. So we'll get some idea of what kind of functionality we want to support, and then also look at what's in the mv.js package. Today we'll start talking about the model view matrix, but later we'll be talking about the projection matrix too. So in older versions of OpenGL, before you were required to have shaders and a lot of functionality was deprecated, matrices were supported, and they were the ones we've talked about a little bit so far, the model view matrix to position objects and manipulate objects and place the camera in the right position, the idea of projection, which will be done through matrices that we'll discuss. And there were also matrices that allowed us to play with textures, as we'll talk about later in the class. And because colors are usually used in 4 dimensions as RGBA colors, if you have some matrices that'll work with 4x4 4-dimensional entities like positions, they can also work just as well with colors. So OpenGL, the older version, said, okay, you also have a color matrix. So the idea was to have different kinds of matrices that would all exist at the present time. So you have this notion of state that's really important to us, that part of the present state was the present model view matrix, the present projection matrix, the present texture and color matrices. And the advantage of doing it that way was you only needed one set of functions to manipulate them. So you would use the same function to manipulate the model view matrix as the projection matrix by just saying that the current working matrix that I'm going to use, that these functions apply to, is now the model view matrix, and later it's the projection matrix. And you'll see a lot of that in our code. It's the same notion as when we did binding and said, okay, now we bind this vertex attribute or buffer, so it's the present vertex attribute buffer. So that goes throughout what we do. And so we selected which one in the older versions by the matrix mode function. Now if we want to do it that way, we have to do it explicitly. So you can say, well, why did they deprecate them? They seem like such useful functions. Why are they gone? Well, the main reason is that these functions operated in the CPU. So what they did is, if you set a model view matrix, that model view matrix would automatically apply to all the vertices, and it would be carried out in the CPU as the vertices were defined by deprecated functions like GL vertex. And so same thing with the projection matrix. Well, what we're going to see is we don't really want to do it that way. If we're going to carry out transformations on a lot of vertex data, we're going to want to carry those operations out on the GPU if we can, rather than the CPU. And so that wasn't an efficient way to do it, although it made the code very nice. Now, what we've done with the MV.js package we've given you is to give you functions that look like they're doing that, but you can now use them to form the matrices and then send those matrices over to the GPU, as we'll see in the next few lectures. So I want to retain the idea of a current transformation matrix because that's a powerful concept. It'll be the current matrix we're using either in the GPU or today in the CPU we will automatically apply to the geometric entities that we apply. So conceptually, it's a 4x4 matrix, and we can look at it from sort of a black box point of view of saying we send the vertex in, and automatically that vertex has that transformation applied to it, producing a new vertex, and you can interpret this as you want as being either the CPU or the GPU, but that's our basic strategy. Now, if we look at how you might want to form and manipulate that matrix, you can come up with a bunch of operations, which for some reason long ago I decided to use this arrow notation just because it's more directly tied to what you're doing in the memory of your GPU or CPU. You're actually replacing what was in there by something. So the kind of operations you could sort of postulate you'd like to have to do graphics is, well, you obviously want to be able to load at least an additional identity matrix. You might like to be able to load or set this. Load mean the same thing here. To set that matrix, current transformation matrix, to be an arbitrary 4x4 matrix. And then since we said we're going to build up our transformations out of simple translations, rotations, and scalings, that we can set that matrix to be an arbitrary translation, rotation, or scaling matrix. Now, if we're going to manipulate them, then we want to be able to change that matrix from its present state by applying a translation, rotation, or scale. Now here's where one of the first decisions come in, is do you do that on the left? Do you do that by multiplication on the right? Do you pre or post multiply? C, some older systems actually allowed you to choose which one you wanted to do, but OpenGL has always taken the position that you post multiply by a matrix. And so we have an operation that says you're going to alter the current transformation matrix by, say, a translation matrix, and what that says, it means that you're going to take the current transformation matrix and multiply it on the right by a translation matrix or a rotation matrix or a scaling matrix or an arbitrary 4x4. So those are the kind of operations we would hope to see supported in our system, and in fact they were supported within the pre-deprecated OpenGLs. So for example, if you did a GL rotate in the older OpenGLs, what that did is it rotated the present matrix, the present matrix mode. So if your matrix mode had been set to model view and you do a rotation, then it's multiplying the model view matrix on the right by a rotation matrix. So you see, it did allow you to use a single set of functions. You had certain kinds of matrices and you just had one set of operations to manipulate them. Okay, so if you looked at something like rotation about a fixed point that we talked about in the last lecture, then it looks something like this. You can start with an identity matrix. You can then move the fixed point to the origin by a translation. Then you do your desired rotation. You see they're all being done on the right, and then you move the fixed point back by doing the inverse of the translation that you first did. Now, if you look at that and do simply substitute in, so if you substitute this CT into this equation, and then you substitute into this equation, you get that in the end, the C is TRT inverse. And this is, again, the seemingly backward order, that the last one specified is the first one that's going to be applied. So this looks wrong, right? So this is how you might try and do it. Say, oh, I know this is going to take me to the origin, but look, it's coming out backwards doing it this way because the first one that's being applied is the inverse one you want. So you really want to do it the other way, which says, okay, first do in your program, see, each of these you can think of as corresponding to one line in your code. First you're going to do the last transformation, then you're going to specify the second transformation, then you're going to specify the first transformation. Now, when you start substituting down, you do get T inverse RT, which is what you wanted. And to go back historically, when people used row matrices rather than than column matrices, as we mentioned last time, then the order came out naturally. But again, it's just contrary to all the physics and engineering literature. So just remember, last one specified is the first one actually carried out. Now, how does this carry on to WebGL? Well, what we're going to do is separate out the positioning of the camera and the objects within the world with one matrix that actually encompasses both the positioning of the objects and the camera, and we call that the model view matrix. And we're going to do the projection separately through another matrix, the projection matrix. So you can think of the current transformation matrix that's being applied to all vertices as being the product of these two, where you're going to apply the model view first to the vertices and then the projection, and this is what you're going to see all along in what we do. But we're going to do what the older OpenGLs did. We're going to have rotation functions, translation functions, and scaling functions to make up these model view and projection matrices. Also, we'll give you some code for the more complicated projections that will be built into MVJS. Okay, so a little bit on how we might use that. So how would we use the model view? Well, the two important ways are, one is to position the camera, because this is how you get the transformation from object coordinates to camera coordinates. You can do it by a bunch of rotations and translations. You don't need scaling generally to do this, but it can get a little complicated. So there's a function called lookat, which in older fixed function OpenGL was in the GL utility library, and everybody used it. It makes it very easy to position the camera relative to the objects. So we built that function and put it into MVJS. We'll talk about it more when we start talking about viewing. We also use the model view matrix to build objects where the parts depend on each other, or just build a model where the parts are in different places, and we need a different model view matrix for each one, so we'll talk about that. The projection matrix, which we'll get to in a week or so, is used to define the view volume and equivalently to select a camera lens, to say where is your camera pointing to, and how much of the world is it really going to see. So that's also going to use the same functionality, but we'll also give you a couple extra functions in MVJS. The strategy, so in conclusion, sort of the strategy is a good one, and we'll look at it this way, is that we're going to get things projected and positioned right by a model view matrix followed by a projection matrix. Okay, let's do a couple of very simple example of trying to do a 30-degree rotation with a fixed point of 1, 2, and 3. So we translate back to the origin. Last one specified is the first one applied. We then rotate by. Actually, I need to redo this example here. So let me break here, and I'll come back, fix this, and come back. Okay, let's look at a simple example. So here we can set an identity matrix by just saying it's a mat4, and that's uses a simple constructor. There's mat3 and mat2 in there. If we want to say multiply that by a rotation matrix, I can do it a couple of ways. One is I could just set a rotation matrix, giving it the axis of rotation, Vx, Vy, Vz, that's the direction, and how many degrees I want to rotate about that axis. So that's the general function. We also built in a rotate x, a rotate y, and a rotate z. So you can say r is rotate x of 90 degrees, for example, which is a little bit simpler. You can look at the code there for rotate and see what it looks like. You can do it that way. You don't even have to define r this way. You can just put rotate in here instead of r if you're not going to use it for anything else. So all of those kind of things are possible. In fact, you can even just do var m equals rotate of this. This is just showing you the operation. Now, by the way, because there's no operator overloading in JavaScript, we had to put in explicit mult functions, add functions, where to do these things. When you look at the code in GLSL that does the same thing, this statement would simply be m star r. But it was that way when we were doing it with C++. But this shouldn't be really a problem for anyone. So here's another example with scaling and translation, and all I had to do was spell translate without this extra letter here. And now we can just multiply those two together. So here's the simple example of a fixed point of 1, 2, 3 and rotating about 30 degrees about the z-axis. So here's the multiplication of a translate. Notice you can chain these all together. I could actually write this all in one line. I think it's a little less confusing. So you're going to multiply together a translation by 1, 2, and 3 times a rotation of 30 degrees about the z-axis, or this could have simply been rotate z 30, 30. And then we have a multiplication of that matrix we created times a translation by -1, -2, -3. And remember, here again is the last one specified as the first applied. So in fact, this is doing what we want. It's moving the fixed point of 1, 2, 3 to the origin, then doing the rotate, and then translating everything back. So finally, one comment or two about arbitrary matrices and how we can use them. What we do in mv.js is we define a 4x4 matrix, and 3x3s and 2x2s are embedded within this structure as a one-dimensional array of 16 elements, because that's very fast to manipulate. So essentially what it's doing is using JavaScript arrays, but we've put in functionality so that you can treat it as a 4x4. What that means is you can address individual elements by it. You can talk about rows and columns, and it's assumed to be in row major order. So first row, second row, third row inside of this one-dimensional array. Now, unfortunately, there's this real confusion in OpenGL between row major and column major, because OpenGL expects its data to be given in column major form. So if you send it 16 elements over to, say, through GL uniform 4F, you will send over the 16 elements. It wants them in column major order. It's a historic thing. We can't change it. You say, well, why don't you do your whole application in column major form? If you want to, you can. But I think most of us are so used to using row major data in engineering and science, we prefer to do it this way. So we decided to do all of our package in row major form, but we put in a flatten function that will automatically, as it sends the data over, it not only strips out all this extra stuff, because a JavaScript array is not simply an array of 16 numbers. It strips that out, but it also changes you from column major, from row major to column major, and so everything should work. So if you simply do things the way you're probably used to with row major matrices, everything's going to turn out right when you use this flatten function. Now, GL uniform, turns out in regular OpenGL, in desktop OpenGL, has a parameter in there that will say, do you want me to transpose this matrix for you to get around this problem? But because WebGL comes from OpenGL ES, which is simpler, that parameter must be false. So you sort of want to say, I don't want to use this flatten function. I want to change it to true, so it'll take the transpose for me. Can't do that. That parameter has to be set to false. Now, finally, just mention matrix stacks. Later on, when we start talking about more complicated models, and we want to have a hierarchical structure, so you have a model that has parts, which has other parts, like a robot or an animated figure, and you want to couple all that motion together, you're going to build up a hierarchical data structure for those models, which will contain in them matrices that tell you how you go from one part to another part. And when you traverse that structure, and this is something you know from basic data structures, when you traverse these kind of tree structures, the efficient way to do that is to maintain stacks so that when you visit a node, you've already seen the information is stored in some sort of stack. Well, fixed function OpenGL had stacks built in. It had a matrix stack for each type of matrix, and all you had to do was do a push matrix or a pop matrix to do that. Well, here it turns out JavaScript here's one of the advantages of JavaScript. It saves you that the arrays, JavaScript arrays, which are what we're using underneath for our representation of our matrices, has a push and a pop built into it. Remember, if you remember back to some of those first examples we did, we said it was much easier instead of using indices to just push things onto an array and it just automatically would create another element. Well, then we could just create a stack by just saying a stack starts off as being an empty array, and then there's a push method and a pop method that's part of the array object. So if I want to put a model view matrix on the stack, I simply go stack.push, model view the matrix I want to put on, and if I want to get it back, I just do stack.pop, and back comes the top element of that stack. So this is another nice thing about JavaScript, is that these kinds of operations, which we're going to really take advantage of later in the course, are built in. Okay, so next lecture we'll start looking a little more deeper at how we actually start using arrays to have actual objects rotating on the screen, how we build up that cube example which I demoed a lecture or two ago.